With questions from yous guys. Anybody got any homework questions? Last time we assigned 1 through 40. Hopefully you got to start on that because it doesn't stop this week, Natalie.
You walk us through number 29.
Sure. So 29 asks us to do u dot w. U is defined as the vector 3, 8. W is defined as the vector the linear combination form vector, negative 2i plus 3j. So first thing I would do is I would convert vector w into a component form. So again, the coefficient on the I is just the x component, and the coefficient on the j is just the y component. And then my definition for a dot product is we multiply the x components together and then add them to the product of the y components. So negative 6 plus 24 is 18. And that's that. Who's next? Natalie.
Number 10.
Okay. So 10 says we want to find the magnitude and the direction for the vectors in the following form, or in component form. Okay. So I'm going to start with the magnitude first, since that's just a formula. So 144 plus 25 is 169, which is just 13. And then to do the direction, I'm going to plot this. So 12, negative 5 is down here. We're looking for this angle. So this guy's my alpha. And the other end of alpha is the 360. So we can say that theta is equal to 360 minus alpha. And alpha is just the tan inverse of the absolute value of y over x. And now it's calculator time. $360 minus tan inverse. And I'm not going to do the absolute values on the calculator. I'm just going to do that part in my head. So I get 337.38.
Okay, thank you.
You're welcome. Blake.
Number 11. Or actually, sorry, number 12.
12? Sure. So 12 says find the component form for the vectors indicated below. Round your answer, blah, 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 blah. So we're given a magnitude and direction. So I know that my component form is just magnitude times cosine of the angle, and then magnitude times sine of the angle. So just plug those guys in, and then it's calculator time. Keeping in mind, though, the angle that I'm given is most decidedly in radians, so I either need to convert that into a degree or just change my calculator to radian mode. I'm going to just change my calculator to radian mode, because it felt like that would be the easier way to do it. So I get 0.73. And then just change that to a sign. And 2.73. And I'm done. Let's change that back to degree real quick before I forget and end up with like all wrong answers throughout the entire lecture because I forgot I put it to radian mode. That's a Mr. Kulik move right there. Hopefully he would have noticed at like some point the answers turned into bat crap crazy, but it is 9:15 or something on a Monday, so you can't take that for granted. All right. Anybody else? Yeah, Alex. Sure. Joe, did you see Mr. Simmons yet?
Yeah.
Okay. He was looking for you earlier. Okay, so 40 says to show that the pair of vectors given are orthogonal. So all we need to do that is we just need to show that the dot product for those two vectors is 0. So again, it's the product of the x's plus the product of the y's. So I get negative 24 plus 24, which is indeed 0. So to show two vectors are orthogonal, all we need to do is show their dot product is 0. And it is. So they are. And we're done. Overall, problems in this section, you know, like if you know what you're doing, they're pretty fast, right? You know? Again, getting comfortable with the notation, remembering some of the operations, takes a little bit of practice, but by the end of this, you should feel pretty good about stuff, you know? Nothing too terribly complicated. Last call on questions. We can always come back and deal with more later, but feels like we were kind of, yeah. What's going on?
You do number
3? So it says that given yada yada yada, find the component form and magnitude for the following vectors. So it wants AB, where A is 3, 1, and B is 5, negative 4. So the vector AB in component form, I'm going to use the head minus tail rule. I can tell B is the head because it's under the head of the vector. So head minus tail, head minus tail. So there's my component form. And the magnitude then is just that. Right? The square root of each component squared.
Okay, I got it. Thank you.
Yep. Or square root of the sum of the components squared, I should say. Blake?
Might I borrow a calculator charger?
You want to? I can plug it in up here, and you can pick it up at the end of class. So, you know, semi-charged up, depending on how long that's going. But I got a couple up here for this reason.
Oh.
What's up? Oh. Okay. Okay. Let's move on forward. So here in section 8.3, we're going to be looking at applications. So we'll start with a very familiar sounding problem. So here we have a boat leaves a port and averages 20 or 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels 55 knots for 3 hours. What is the distance and bearing of the boat relative to the starting position at the port? So again, it's a problem we've basically already done, correct? So I'm going to have two vectors. I'm going to call them u and v, just for boat 1 and or for part 1 and part 2 or whatever. So the magnitude for part 1, we were doing 40 knots for 2 hours, so 80 nautical miles. And then we're doing 55 knots for 3 hours, so 165 nautical miles. And then if I want a bearing of 215 degrees, remember bearings start north and they go clockwise. So 215 degrees is like here. But we really want this one, right? So 90, 90, and then 55. So that's 235. And the same thing here, our bearing at 162. So over here. But we want this one. So 90, 90, 90, and then 18. So our bearing there is 288. So I'm going to resolve vector v into component form now. And I'm going to do the same thing for vector u. Put it into component form. And then I'm going to do u plus v. So that is going to be adding the x components. So 510. And then adding the y components. Uh-oh. Oh no. Oh, I see I have an extra parenthesis in there. There we go. So that's negative 222.46. So the magnitude of that then is just the square root of the sum of the components squared. So that gives me 22251. So nautical miles. And if I draw my picture here, so 5 over and 220 down, it's like here. So we're looking for this angle here. There's my alpha. The other arm of alpha is made by 360. So theta is 360 minus alpha, where alpha is the tan inverse of 22251. Oh, I'm sorry, 46. Excuse me. Negative. Divide by 5.10. Absolute value of that. Let's put the absolute value in there. So that gives me 271.31. Or if that's a bearing, that would be that this little angle here is 8.69. So that would be a 98.69 bearing. Depending on what we were asking for in the question, it didn't state. Oh my goodness. That's not right. That should be 88.69. Cheapers creepers. So that's 178. That didn't make a lick of sense when I looked at my picture. And this is a rehashing of a problem we've already done, right? We did this first semester. We should have been okay at this. Hopefully we still remember doing it. So the next idea, we're going to define another new vector operation called a projection. So I'm going to draw a little bit of a picture first. So let's say we have some vector u, and then some other bigger vector v. What we'd want to do here is we'd like to be able to project an image of vector u down onto vector v. So to do that, basically we're going to drop a perpendicular bisector down, and this vector here that's in the same direction as v, we're going to call the projection of u onto v. So that's kind of our definition for what a projection is. And one thing I'd like to point out to you here is if we call this perpendicular side vector W, we should observe that the projection of U onto V plus vector W should be equal to vector U. That's just our definition of vector addition, right? If we add two vectors head to tail, the resultant is the sum. Or I could say that this vector W should be equal to U minus the projection of U onto V. Jillian? Correct. Absolutely not. Yeah. So, what is this projection of U onto V really representing? It's basically describing how much of vector U is applied in the same direction as vector V. Now, this is an important concept when you talk about specifically in physics, right? If you're talking about, hey, I have some force going at this angle, pushing against this thing, like how much of the force is actually being applied in this direction. These become important kind of physics questions. But basically that projection of U onto V is saying how much of U is being applied in the same direction as V. Okay with that idea? Okay, so how do we actually go about calculating this projection? So if we're given some non-zero vectors, U and V, we say that the projection of U onto V is equal to the dot product of U and V divided by the magnitude of V squared times vector V. So that's our formula for how we actually go about calculating that projection. Okay, so some finer points here talking about this formula for the projection. So notice in this problem, or this situation that we drew up above, I drew V like arbitrarily big, right? Like that's just really big. And it appears that size of vector V does matter. And, well, it kind of does and it kind of doesn't. Depending on what you're trying to do, there's a lot of cases where really all we care about for v is its direction, and we can just assume the magnitude for v to be 1. And then the other thing to point out to you guys is this piece, u dot v over the magnitude of v squared. U dot v gives a real number because it's dot product. And the magnitude of v squared, also just a real number. So what we're really doing here is just a scalar multiplication, right? It's basically scaling u to fit it on top of v. Is essentially all we're doing here. So we're basically just scaling this vector v. Okay, so let's do some examples here to start getting comfortable with this whatever majevers. So it says, find the projection of u onto v, and then to express vector u as the sum of two orthogonal vectors, one of which is the projection of v onto u. I'm sorry, the projection of u onto v. So let's start by doing the first part. So the projection of u onto v is going to equal the dot product of the two vectors divided by the magnitude of the vector you're projecting onto squared times the vector. So we'll start by just doing the dot product. So that's 14. And then we'll do the magnitude of v. So that's 36 plus 16, which is 52. So then notice that I'm not going to bother rationalizing or simplifying that radical, because really what I care about is v, or the magnitude of v squared. So I can just drop the radical when I find the magnitude of v squared. So 14 over 52 really reduces down to 7 over 26. So when I do that, what do I get? I get 21 over 13, and then I get negative 14 over 13. Everybody's okay? I reduced the fractions as I multiplied. I promise that's right, though. So we did that part of the question. Everybody agree? Jillian?
How'd you do 7 on top of the...
So 14 over 52 reduced down to 7 over 26.
Oh,
What we still need to do, though, is to do that, right? We still have one more part of the question. So what I'd like to draw back on is this picture that we drew earlier. So there's V, here's U, here's my projection of U onto V. And this is going to be what we'll call vector W. So what I can say then, again, is the projection of V onto U plus W is equal to the magnitude of U. Or, I'm sorry, is equal to vector U. So this projection, we know, that was 21 over 13, comma, negative 14 over 13. W we do not know. And U we know is, what was that? 3, 1. Everybody okay with everything that I've written so far? If I need to stop and explain something more, please tell me. We can slow down, or if you need a minute to catch up, or you're not sure, stop me and ask. It's okay. Okay. So to get the W by itself, I'm just going to subtract the projection over to the other side. So 3 is 39 over 13, and 39 minus 21 is 18. 1 is 13 over 13, and 13 minus a negative 14 is 27 over 13. So what I can do now is I can say U is equal to my projection, which was 21 over 13, comma, negative 14 over 13, plus this W, 18 over 13, comma, 27 over 13. And I know that these two vectors, the projection of U onto V and this vector W, are orthogonal because of the definition of the projection. So this is indeed my answer to that question that was highlighted in green. So it basically just boiled down to doing a little bit of vector subtraction to find that other vector that was orthogonal to the projection and who adds up to give us W. Or adds up to give us U, excuse me. So another way of thinking about what this projection idea is, what I've done here is I've taken U and broken it up into two orthogonal pieces. That's another way of thinking about this, which is exactly what we did when we put things in linear combination form, is we took a vector and broke it into two orthogonal pieces. Now that's a heck of a lot more trivial than this was, but okay. Let's do another example. Yes, of course.
In the problem, it expresses.
So in the
But they mean yeah.
those are
Oh, it's just super. Okay.
they are wedged, but that's just what the typeface wedge looks like. No, totally fine. Totally fine. These are important questions and like important things to make sure you have straight, because we've made a big deal out of the notation being important, and that, you know, a bracket and a wedge and a parenthesis are imply different things. Okay. So this story problem is another case where we're going to be using projections. It says Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? So I'm going to start by kind of drawing myself a picture. So I'm going to start by drawing my hill vector. And I know if the angle of incline is 25 degrees, that's basically saying that, like, this piece is 25. But what I'm more interested in is really that that piece is also 25 degrees. Oops. Everybody's okay with that? Okay. I guess I probably should have color-coded that. Let's do that. Okay, so that's our first vector. That's what we're going to be projecting onto, right? Because we want to know the amount of force sliding down the hill. So we're going to be projecting onto the hill. Does everybody feel okay with that? Our other vector is the weight of Kyle and the sled. What kind of force is just a person generating if they're just standing straight? Gravity. And which way is gravity pulling? down. So I'm going to call that G. So what we're looking for then is this projection here. So I drew this really detailed picture so it's clear that you guys can see what we're doing. We can develop a little bit of intuition about like how to do these problems. Is this picture necessary to do the problem? No, but where you guys are at, starting from never having seen anything like this before, I would recommend drawing the picture. I think it's really helpful in helping to make sure things are set up right. But once you got the hang of things, you don't really need the picture here. Does that feel okay? All right. So I'm going to start by taking my vector h and creating a component form vector for this. Now, in this problem, are we told anywhere the length of the hill? No. So guess what we can assume that the magnitude of h to be? 1. So then I just need to get the direction of h. Which is going to be 335, right? Just 360 minus 25. Does that feel okay? So there's my magnitude, or my vector for h. Feel good? Next up, I'm going to find the vector for g. So the direction for g straight down is 270 degrees. And we know the magnitude of g is 165. Now, probably some of us could have looked at that and gone, Mr. Kulik, isn't vector g just going to be 0, negative 165? Yeah, sure. Absolutely. Since the arrow's pointing straight down and the magnitude is 165, like, doy. But I think it's helpful to kind of just reinforce the formulas and kind of what we're doing, that we're not just doing this all willy-nilly, that we're plugging stuff into formulas and we're doing it the exact same way every time. Now, if you see that shortcut and you'd like to take it, you're welcome to do that. You don't need to write out that step. But I think the first time doing it, it's helpful to see that. And then cosine of 335. And then sine 335. So 906 and negative 423. So far, so good. Okay, so we want the projection then of G onto H. So that's going to be H dot G divided by the magnitude of H squared times the vector H. So that's negative 6973 over 1. So far, so good. Notice that I didn't worry about the 0.906 because it's just being multiplied to 0. So that's 0, right? When I did the dot product, I just did the dot product in my head there real quick. Okay. So then I have this times this. So negative 6320. I have this times this. So 2947. I forgot it already. 2947. Yeah. Yes. That's the dot product of H and G. So I did 0 times 0.906, which is nothing, plus negative 0.43 times negative 165. Oh no, how did I get a negative there? I forgot the negativeness, so it should be positive here. Positive. So that's positive. And oh, that should still be negative. Excuse me. Thank you for catching that. Oops. Everybody feel okay? And now, if I want the amount of force going down the hill, I'm just going to be taking the magnitude of that projection vector, because that's the amount of Kyle and the sled that is heading down the hill, right? That's the portion of that vector that's actually going down the hill. So the magnitude of that will tell me the amount of force that's actually going down the hill. Oh, that's 6320, not 6920. Mr. Kulik, get your stuff together. Well, you know, it's early. What's up? Whoa, that's bonkers, huh? Time flies when you're doing math. So I get 6973. Okay. Can I point something out to you? This 6973, did we see that number before? It popped up there as the dot product of G and H, right? So here's my question for you. If U is a unit vector, which is what we had here for H, right? Is the magnitude of the projection of V onto U equal just the dot product of U and V? Because that's what we're observing here, right? H was a unit vector, so the projection of onto that unit vector just, or the magnitude of the projection onto that unit vector was just the same as the dot product. Well, let's see if that's indeed true, right? So let's try to prove this. Seems like it's true. At least it was true in this case. Let's try, right? Because if that's the case, that's a pretty nice shortcut for the problem, right? If things ended right there at the highlighted section, you didn't have to do any of that extra mumbo jumbo. Okay. So the formula for the projection of U onto V was U dot V divided by the magnitude of U squared times U. See ya, Garth. Okay, so if U is a unit vector, we know the magnitude of U is just 1. Everybody agree with that? And we know that the dot product, U times V, is just a real number. And we had talked about how we can pull the real number outside of a magnitude. And we know the magnitude of U is just 1 because it's a unit vector. So yeah, that is the case. So that presents us with a nice shortcut when we're projecting onto a unit vector, right? Is the magnitude of any projection onto a unit vector is the same as just the dot product of the two vectors. That saves us a bit, right? That's helpful. Let's do another example. How's the pace here, guys? Are we going reasonably fast or reasonably slow, I guess is the question. This isn't not bulldozing you guys, am I? I feel like I'm trying to do this very slowly and carefully because I know this is not trivial what we're doing, right? I don't want to just feel like, oh, Mr. Kulik's just bulldozing me. And I did a little bit of bulldozing probably last class because the things weren't nearly so complicated. But what we're doing now is like not trivial at all. Okay. So here, a crate is being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assuming that the crate is of negligible weight, what is the amount of force directed up the ramp? So again, I'm going to go ahead and draw my picture here. So I have my crate. Being pulled up the ramp at a 40-degree angle. And then I have the ramp that's 10 feet horizontally and 2 feet up. So maybe that. Well, actually, let's do it like that so it makes a little bit more sense. And then we're looking for this guy, the projection of the crate onto the ramp. So I have two vectors to create. I have the crate vector and then the ramp vector. So the crate vector, I'm just going to use my formula for component form, since I know that the magnitude of the crate is 100 and the direction is 40. That's easy to do. Everybody's okay with that? And what's the component for the ramp going to be? Are we given a magnitude and direction for the ramp? No, but we don't need it. We're given something better. We're given its horizontal and vertical component. So if it's 10 feet horizontally and 2 feet vertically, shoot, Mr. K, that's nice. We feel good with that? Now, observe, are we projecting onto a unit vector? We are not, right? Clearly, the vector 10, 2 is not going to have a magnitude of 1. So this means we're going to have to do the full-blown, there's no stopping early. Okay? So projection of crate onto ramp is going to be the dot product of the crate onto the ramp divided by the magnitude of the ramp squared times the vector ramp, or times the ramp vector. So, well, let's just do it on the calculator, right? C dot R. So I have 100 cosine 40 times 10 plus 100 sine 40 times 2. So I get 894.6. I guess I probably want to, 060. Okay. The magnitude of R squared is just going to be 10 squared plus 4, or 2 squared, excuse me. I don't have to worry about the square root because the squared just gets rid of the squared root. So I have 894.6 divided by 104 times 10. And then the same thing times 2. So I get 8601 and 1720. Oh, 8602. Sorry. And then my last step then is I just need the magnitude of that vector. Oops. And I get 8772. Pounds up the ramp. This feels probably like the place to stop, right? This was not trivial what we've been doing. I can't finish the next section in 20 minutes, nor would I really think that's wise. So let's just stop here for today. At this point, you could add in 41 to 50 to your problem set. And you guys still have, I don't know, 15, 20 minutes here to kind of get chucking away at these things. My suggestion to you is I would take that 15 or 20 minutes right now and try to do a little bit of this 41 through 40. Even if you haven't done the stuff before it, try to do some of this stuff right now in particular. Make sure that you can do the projection. Make sure you can do one of the story problems. If all you finish is one of each, I'd consider that a good use of this time to just try to cement that process a little bit for you. Okie dokie.